Hi, I'm Bob. Today, let's continue to solve the problems from 7 to 12 at the end of Chapter 2, the simple linear regression model in the textbook Introductory Econometrics, a modern approach, the 7th edition. Here's the problem number 7. Consider the savings function, where e is a random variable with the expectation equal to 0 and variance equal to sigma squared. Assume that e is independent of income. The first question is to show that the expectation of mu conditional on income is 0, so that the zero conditional mean assumption is satisfied. Here's my solution. The expectation of mu conditional on income equals the expectation of squared root income times e conditional on income. We treat income as constant and take it out of the expectation. Since e is independent of income, the conditional expectation of e equals the unconditional expectation. So the expectation of e conditional on income is 0. Then the expectation of mu conditional on income is 0. The second question is to show the conditional variance of mu. We can write the variance of mu conditional on income as the variance of squared root income times e conditional on income. We treat income as fixed and take it out of the variance. Since e and income are independent, the conditional variance equals the unconditional variance. Therefore, the variance of mu conditional on income is a function of income. It increases with income. The homoscedasticity assumption is violated. The variance of the outcome variable savings equals the variance of mu, and it increases with income too. The third question is to give reasons to support the assumption that the variance of savings increases with family income. Low-income families have to spend on consumption and have little to save, while high-income families have more choices on their income. They can save more and spend less, or save less and spend more. The variation in savings for high-income families is larger than that for low-income families. So the variance of savings increases with income. Let's go to problem 8. Consider the standard simple regression model. Under the Gauss-Markov assumptions, the usual OLS estimator, beta hat 1 and beta hat 0, are unbiased for their respective population parameters. Let beta tilde 1 be the estimator of beta 1 obtained by assuming the intercept is 0. The first question is to find the expectation of beta tilde 1 in terms of the x, beta 0 and beta 1. Verify that beta tilde 1 is unbiased for beta 1 when the population intercept beta 0 is 0. Are there other cases where beta tilde 1 is unbiased? We use the OLS estimate formula for beta tilde 1. Then we replace yi with its true relationship with xi. We rearrange the numerator and write it as 3 terms. The expectation of beta tilde 1 conditional on x is as follows. The last term is 0 because of the 0 conditional mean assumption. So the expectation of beta tilde 1 has 2 terms, beta 1 plus beta 0 times the sum of x divided by the sum of squared x. Generally speaking, beta tilde 1 is a biased estimate of beta 1 except in 2 cases. The first case is that beta 0 is 0. The second case for an unbiased beta tilde 1 is that the sum of x is 0, or equivalently, the sample mean of x is 0. In this case, the point of the sample means is the origin. The OLS fitili goes through the origin. The second question is to find the variance of beta tilde 1. Here's my answer. We use the beta tilde 1 formula again and substitute yi with its expression. The variances of the first 2 terms are 0, conditional on x because they are constants. For the last term, we write the x terms out of the variance sign. And finally, we have the answer. The variance of beta tilde 1 is the variance of the added term sigma squared divided by the sum of squared x. The third question is to show that the variance of beta tilde 1 is smaller than or equal to the variance of beta hat 1. We write down the expressions of the 2 variances. We need to compare the 2 denominators. Write out the squared term. Using algebra, we can write it as the sum of squared x minus the number of observations times the squares of the sample mean, which is smaller than or equal to the sum of squared x. So the variance of beta tilde 1 is smaller than or equal to the variance of beta hat 1. The fourth question is to comment on the trade-off between bias and variance when choosing between beta hat 1 and beta tilde 1. Beta hat 1 is unbiased, but has a larger variance than beta tilde 1. Beta tilde 1 has a smaller variance, but it is a biased estimator. One way to compare estimators that are not necessarily unbiased is to compute the mean squared error, MSE, of the estimators. If W is an estimator of beta, then the mean squared error of W is defined as the expectation of the squared bias. The mean squared error measures how far, on average, the estimator is away from the true parameter beta. We can write mean squared error as the sum of the variance and the squared bias. Mean squared error depends on the variance and the bias. It allows us to compare two estimators when one or both are biased. Here, beta hat 1 is an unbiased estimator. Its mean square error is just its variance. For beta tilde 1, its mean squared error contains two parts. In the above questions, we have got each term's expression. The difference between them depends on the variance of the error term sigma mu squared, the intercept parameter beta 0, and x. Let's go to problem number 9. The first question is about how changing the units of measurement of the outcome variable or the explanatory variable affects OLS estimates. Let beta tilde 0 and beta tilde 1 be the intercept and slope estimates from the regression of C1yi on C2xi. Using the OLS estimator formula, we put the scaled versions of x and y and find how beta tilde 1 and beta tilde 0 relate to beta hat 1 and beta hat 0. Beta tilde 1 equals C1 over C2 times beta hat 1. Beta tilde 0 equals C1 times beta hat 0. It verifies that OLS slope and intercept estimates are multiplied by the constant C1 if the outcome variable is multiplied by C1. If the explanatory variable is multiplied by a constant C2, the slope estimate is divided by C2, but the intercept estimate is unchanged. Another method to show the result is to write the original equation first, and then times C1 on both sides. The left-hand side becomes the new outcome variable C1 times yi. We can write the new explanatory variable C2 times xi by multiplying and dividing by C2. Now we have a simple linear regression model with a new explanatory variable and a new outcome variable. We can write the beta tilde 0 and beta tilde 1 directly as a function of beta hats C1 and C2. The second question is to regress C1 plus yi on C2 plus xi and show the OLS estimates. I plug the explanatory and the outcome variables into the OLS estimator formula and show the beta tilde 1 equals beta hat 1. Beta tilde 0 equals beta hat 0 plus C1 minus beta hat 1 times C2. We can also use another method to obtain the same answer. The trick is to arrange the new outcome variable and the new explanatory variable without changing the equal sign. The third question. Let beta hat 0 and beta hat 1 be the OLS estimates from the regression log yi on xi. Let beta tilde 0 and beta tilde 1 be the OLS estimates of intercept and slope from the regression of log ci yi on xi. Show them. I use the method of rearranging the equation. To make the new outcome variable, we need to add log C1 on both sides. Comparing the new equation with the original one, we can write the new OLS estimates that relate to the original estimates. For the fourth question, we need to rearrange the equation to have a new explanatory variable log C2xi. To do that, we subtract and add beta 1 times log C2 on the right-hand side. After rearranging the equation, we can write the OLS estimates directly. From part 3 and part 4, we know that if the outcome variable is in the log term, or the explanatory variable is in the log term, changing the units of y or x will not change the OLS slope estimate. We could prove that in a log-log model, changing the units of both x and y will not change the slope estimate. Let's do the 10th problem. Let beta hat 0 and beta hat 1 be the OLS intercept and slope estimators, respectively, and let mu bar be the sample average of the errors. In question 1, we are asked to show that beta hat 1 can be written as follows. We write a formula for the OLS estimate of the slope beta hat 1. Then we substitute yi and y bar with their expressions. After some algebra, we can write it as beta 1 plus a term. And we continue to write it into 3 terms. The last term is 0. Then we denote part of it wi. And we come to the answer. The second part is to show that beta hat 1 and mu bar are uncorrelated. We use the hint. To show the expectation is 0, we use the answer from the first part to write it out. Finally, we need to show that the sum of the deviations from the mean is 0. It holds. In the third question, we will show that beta hat 0 can be written as beta 0 plus mu bar minus beta hat 1 minus beta 1 times x bar. We write the formula for the OLS estimator beta hat 0. Replacing y bar with its expression and rearranging the terms, we have the answer. The fourth part asks us to show the variance of the beta hat 0. We use the beta hat 0 expression from question 3. There are 3 terms. The variance of the first term is 0 because the variance of a constant is 0. The second term is the variance of mu bar. It can be shown that it equals 1 over n times sigma mu squared. For the variance of the third term, we treat the x bar as a constant and take it out of the variance sign. The variance of a variable, beta hat 1, minus a constant, beta 1, equals the variance of that variable. Finally, we reach the answer. In the fifth question, we simplify the expression in part 4. We factor out the common part, and the terms inside the parentheses can be simplified, and the final answer can be found. Here is the 11th problem. Suppose you are interested in estimating the effect of hours spent in a SAT preparation course on the total SAT score. The population is all college-bound high school seniors for a particular year. The first question is that suppose you are given a grant to run a controlled experiment. Explain how you would structure the experiment in order to estimate the causal effect of hours on SAT. I will design a controlled experiment to randomly assign hours spent in a SAT preparation course to students. The assignment must be independent of the students' characteristics, such as ability, health, diligence, personality, family background, and so on, that affect her test scores. The zero conditional mean assumption is satisfied in this way, and a simple linear regression of the SAT scores on the hours of preparation course can give us the ceteris paribus effect of the hours on SAT scores. The second question is to consider a more realistic case where students choose how much time to spend in a preparation course. List 2 factors contained in mu. Are they likely to have a positive or negative correlation with hours? If the students choose how much time to spend in the preparation course, the hours spent will be correlated with the students' unobserved factors that affect SAT scores. The unobserved factors contained in the error term include the student's health and whether the student is lazy. The student's health is positively correlated with hours spent in the SAT course. A less healthy student is more likely to be absent from class. Whether the student is lazy is negatively correlated with the hours. The third question is about the sign of beta 1. Beta 1 should be positive. 1 more hour of the course increases SAT score by beta 1 points on average, other factors being equal. The fourth question is about the interpretation of beta 0. Beta 0 is the average SAT score for students who did not take the preparation course. Let's go to the 12th problem. It is about a regression of y on only an intercept. The first part is to show that the OLS estimate of the intercept parameter is the sample mean. We use the standard method to find the OLS estimate. We minimize the sum of squared residuals. The first order condition is to take the first derivative with respect to the only choice variable beta tilde 0 and make it 0. Finally, we can show the answer. Beta tilde 0 equals y bar. That is, the sample average minimizes the sum of squared residuals. The second question is to argue that these residuals always sum to 0. We remember that the first property of OLS statistics is that the sum and therefore the sample average of the OLS residuals is 0. It is true when there is only an intercept in the model. Here's the proof. We write the residual as yi minus beta tilde 0. The first order condition implies that the sum of yi minus beta tilde 0 is 0. We can see it clearly in question 1. So the OLS residuals always sum to 0. The above are the solutions to problems from 7 to 12. I hope they help. See you. Thank you for watching this video and subscribing to my YouTube channel. See you next time.